In this video, we're looking at question 2 of the derivatives in mechanics problem set. We're told a skydiver of mass m opens her parachute and finds the air resistance. F sub a is given by this formula, F equals bv, and we've discussed in class that this means the force is equal to a constant times the magnitude of the velocity, but in the opposite direction. We're asked, draw a free body diagram for the skydiver. So we've discussed the force of gravity on the skydiver is equal to mg and is downward, and the force of air resistance is equal to bv and is in opposition to the velocity. So if she were moving up, this force would be down, but she is falling, so this force is upwards. Remember, we discussed we can define the velocity in this to be such that downward is positive, so we'll have force of gravity is positive and force of the air resistance is going to be negative in this case. Part B, use Newton's second law to set up but do not solve a differential equation for her velocity as a function of time. Here we see that F equals ma, F net equals ma, so m times the time derivative of velocity. This makes it a differential equation that we put a derivative in here. Mass times acceleration is equal to mg minus bv. That is the net force. So if we divide everything by m, we see that dv dt is equal to g minus b over m times v. Very similar idea in part C. We're asked for a differential equation again, but equation for distance as a function of time. Here we see that, well, velocity is the time derivative of distance, so this is the derivative of position. So, the acceleration is the derivative of position with respect to time, so that's d squared x dt squared. That is a equals g minus b over m, and v is dx dt. So we've taken this same equation and written it in terms of the function x, but still with derivatives with respect to time. Find terminal velocity in terms of m, b, and g. Here we just want to say, when will the velocity become terminal? When will it stop changing? Well, by definition, when dv dt, the derivative with respect to time, is equal to 0. So just set that equal to 0. 0 equals g minus b over m times v, and solving for v shows us that that's equal to mg over b, that is v terminal. Part E, in a different situation, we're given this different expression for the air resistance, so then our net force is going to be mg, and the air resistance is minus bv plus cv squared. That is the net force, and that's equal to ma. So setting a equal to 0, dividing everything by m here, we see that 0 is equal to g minus b over m v plus, minus, distributing this minus sign, minus c over m v squared. So we have coefficients for our squared term, linear term, and constant term here, and we just want to find the roots of this equation where the velocity, rate of change of velocity will equal 0. Applying our quadratic formula, we see that v is equal to negative this constant, so b over m, negative is a positive, plus or minus the square root of b squared, so that's b squared over m squared, minus 4ac. A is a negative term here, so minus 4ac is going to become a plus 4 times a is c over m, and c is g, all over 2a. So that gives us values for the terminal velocity in the case of this more complicated form for the air resistance. We'll look at how to solve part F in a separate video.